Hello, hello. Do you hear me? Please reply if you do hear. Okay, very good. I don't know why camera and video doesn't come, but I think slides will be okay. So I will speak slower because of this feedback. But if you do have questions, please let me know, stop me and ask questions. I will be hearing for the feedback. Okay, thanks for coming. So slides are. Do you see slides? Are they reproduced in a good quality? Okay, and I believe I have sent them, and you should have them on your um, screens if you want. They were sent by email. So here are standard beginning slides for the goals of the course, and today will be lecture number 11, which is part of the chapter on Hartree-Fock theory. So we have completed the background information, and today we will slowly start the philosophy of Hartree-Fock theory by slow steps. And here is the link for the recording from previous year. So here are your votes for presentations on Thursday next week. And if you want to add something, if you missed to sign up, please send me an email. If you did send it within the last 5 minutes, I may have missed it. Okay, and thank you for those who completed the homework. If you were busy with something else, just add new assignment to this one and submit it when you have time. So the additional assignment is based on what we did in the lab, and it will be building these two models and compute some basic things like report interatomic distances, total energy, ionization energy, electron affinity, and plot few orbitals. So for the submission of homework, try to accumulate all this information to the Word or PowerPoint file and either print it or send electronically. So if you want to stop me and if there are some questions to answer, please speak loudly, because I may not hear well from the distance. So there is an idea that we need to cover today, and it will be not much derivations, but there will be new concepts. So there is an image that I inherited from previous years. So suppose that you do have blue circles corresponding to positive nuclei. So there are no electrons, only nuclei. And then you throw in one electron. Let's say the first electron has a red color. Then this first electron if the nuclei stay close enough to each other, then the electrons would the first red electron will electron in different space locations, all of which will be nearby of these blue ions. So the closer to the ion, the higher probability to find an electron. And it is not a rigorous consideration. It is only for the concepts. Kevin, you are departing?
Yeah, I'm going to listen on my cell phone.
Okay. So suppose that this red curve is approximate area of space where first electron is located, so it can has probability to be near each of the ions. Now let's do an experiment in our mind, assuming that we submit a second electron to this molecule. Okay, so this second electron will not like the areas of space where the first electron is already residing. So it is a black curve. So the second electron will try to come closer to ions, but it will not be able to come to the spots that already occupied by probability of first electron. Of course, what I'm telling right now is oversimplified and not generally correct, but it gives approximate idea what to expect. So due to electron-electron repulsion, each subsequent electron submitted to the molecule will sit on a different probability distribution, on a different orbital. So again, in this figure, we completely ionized the molecule and then started submitting electrons one by one. And we, through simple logic, through intuition, we see that they would repel each other and come into different spatial positions, different distributions. Please feel free to stop me if you object, or if you want me to repeat something. So this is the last slide that we are going to see today. And here is the idea. When we did everything before, and I may give a little brief overview of previous two lectures, but recently we started focus on electronic part of molecular Schrödinger equation, and we realized that electronic wave function does depend on many independent variables, on positions of each electron, and it is too complicated. We already agreed that atomic orbitals are our building blocks, and Slater determinant is our blueprint. And there is one missing concept in this plan. Between atomic orbitals and Slater determinant, there is one more concept, molecular orbitals, that we will slowly introduce in class, but you are already doing it in lab and in homeworks. So there is a goal to jump from electronic Schrödinger equation for many electrons to specific equation, which may look like Schrödinger equation, to single electron states, to objects that we will later call orbitals. If electrons would not repel each other, it would be super simple. But they repel each other, and therefore there is a big challenge. So in this last slide, you see there are two lines. And let's, for a time, forget everything that you see in the curly brackets. So let it be some unknown operator. But after curly bracket, you have phi sub 1. So it is unknown wave function for the first electron. In the second line, after curly bracket, you have phi sub 2. So it is equation for unknown wave function for the second electron. And as soon as we solve these two equations and get functions phi 1 and phi 2, we can combine them together according to procedure of Slater determinant, or as a simplification, even as Hartree product, and generate approximate multi-electron wave function. So once again, the goal is to jump from many electron wave function, which is hard to solve, to one electron wave functions for each electron, which are easy to solve. And the goal of today's meeting is to discuss and agree on the stuff that is enclosed inside this curly brackets. So if you agree with this idea, you are kind of done. The rest will be technical details. So feel free to stop me, or probably I will even see if you raise hands. Okay, no one is raising hands. Where is the button for next slide? Okay, here. So when we met two previous times, we agreed on this form of Slater determinant that represents anti-symmetric wave function that forbids to place two electrons into the same state. And our general map to study Hartree-Fock theory is to use some background about spin, Slater determinant, bring in concept of mean field correlation and exchange, and then there will be flow chart similar to what we did for optimizing geometry. So on this map, we are in the between top box and next and second box. We are in the mean field. So we are slowly coming to a concept of the mean field. Okay. So, and this is just a reminder. So as soon as we nailed down positions of nuclei, we solve Schrödinger equation with three terms: kinetic energy of electrons, electron to nuclei attraction, and electron to electron repulsion. And later we agreed that atomic wave functions have four indices: principal, orbital, magnetic, and spin. And we are done at addition of spin 1/2 that gives singlet with superposition of both first and second spin with these factors. Okay. So the goal is to formulate equations for one electron objects, which will be our larger units, larger building blocks to form multi-electronic wave function. And through this little oversimplified figure and through common sense, we came to the idea that if we submit more electrons to the molecule, they will interact with previously submitted electrons. And the influence of these previously submitted electrons affect the shape of spatial distribution of each next submitted electron. So Yeah, let's skip it. It's too this will be right. So you all already know that multi-electron wave function that depends on Cartesian position of first, second, and so forth electrons is Slater determinant. Today, just as a little simplification to finish in time, we will use Hartree product, just a product of wave function 1 for electron 1, wave function 2 for electron 2. But we do need equations for this phi 1 and phi 2 wave functions. So, of course, except H2 molecule, there are not very many molecules where we have 2 electrons. It's not a good example for in the general case, but we need to start from something simple. So in some sense, we are trying to solve the equation that is shown right now. So Hamiltonian includes 3 terms, and wave function is a product. Wave function that depends on 2 electrons is a product of 2 1-electron wave functions. So operator, product of unknown wave function, unknown energy, product of unknown wave functions. So we are going to use a property that if wave functions are well defined, they should maintain orthogonality property. The goal is to jump from this equation for 2 wave functions in product form to only 1. So what if we practice a concept that Mary was asking to declare on the previous meeting? We need to practice a concept that converts operator and quantum state into a number. So can you guess what is which word is hidden under these orange boxes? Ben? Yes? I didn't hear. Nathan? Oh, perfect. Okay. If no one would say it, we would need to play a game and remove one by one boxes and finally guess the word. Yes. It's expectation value. You won. So if you multiply operator, not multiply, convolute with Brian Cat from left and right, you will get a number. But here we are doing a trick, a really unusual trick. So typically, we play with 1-electron operators, and our wave functions in the introductory classes are also depend on 1 electron. So the number of independent variables for operator and electron is the same. So if you practice the protocol to find expectation value, you are converting operator and wave function into a number, right? But now we will do partial expectation value. So we'll do average over 1 independent variable and keep another independent variable active, explicit. So if you see lower line, our operator A, and someone asked why A, because arbitrary in general. If it depends on 2 independent variables, R1, R2, and we dress it with wave function which depends only on position of second electron, then the resulting object will be not a number but a new operator that will act only on independent variable R1. Do you want to protest against this idea? Okay, good. No one protests. Means everyone is happy. Okay, so this is probably most important slide. So if you are debating to take notes or not to take notes, it is probably the most important one, which is justified to take notes. So let's look on the first line, and let's assume that you do not see red color. Otherwise, it will be too many things to explain. So top line with equation and no red color. Then it is the same thing that we had before. So kinetic energy of electrons, attraction to nuclei, electron repulsion acts on 2 electron wave function equals energy times 2 electron wave function. Now, so here is the key thing, most important in the whole lecture. Let's play a game. Let's and all wave functions were in the cat form. Now let's multiply left and right part by bra from the left. So if you agree with this idea, if you do not protest right now, the rest will be just technical consequences. So now suppose that you see a movie like this phi sub 2 bra appears from the left to both sides of equation. So if you do see such construction, it means, you know, the bra and cat means integration over a variable which is inside them. Like if it is 2, it is integration over R2. So if we follow the rest of lines, we'll see the following thing. Before we practice this red bra vector, in the brackets we used to have Hamiltonian for 2 electrons. That depends on 2 vectors or 6 Cartesian projections. After we write this little red thing, it means we integrate out 3 dimensions, and the object on the left side of equation will be neither many electron operator nor a number. It will be operator of reduced dimensionality. It will be operator that will act on variable R sub 1 only, because we have completed integration over variable R sub 2. So if you see the second line with equation, you see that there is a kinetic energy with bra and cat of phi 2 on the left and right, attraction, nuclear attraction with phi 2 on the left and right, and electron repulsion with phi 2 on the left and right. So this object in the round brackets will be one electron operator that will be acting on unknown function phi 2. Now let's look on the right side. So the the E, unknown energy, is not an operator, it is energy, it is number. So we can pull it out of the bra and cat convolution. And this phi 2 bra and phi 2 cat, due to orthogonality, will give 1. So we can cross out this term. And then this equation again gets a form of Schrödinger equation for unknown function phi 1. Any objections or questions? Not yet. Okay. Let's look further. So what I'm going to do next, you do see that there are three terms in Hamiltonian. So probably I may want to carefully plug in, carefully open these brackets for kinetic energy, nuclear attraction, and electron repulsion, and see what happens. This is one thing. Second thing is to repeat the same procedure, but the red object in the top line in form of bra vector will be not phi1 but phi2, so that we not phi2 but phi1, so that we integrate over phi1 and obtain an equation for unknown one electron function for the second electron. So with this trick, instead of one complicated equation that depends on 6 independent variables, we will obtain two a little simpler equations for 3 independent variables, two one electron equations. If we complete this task, it will be a really big success. Okay, we started half an hour ago. So let's look on the kinetic energy. So kinetic energy for multi-electron wave function did include, you know, the second derivative over position and x, y, and z. And it is x1, y1, z1 for first electron, and x2, y2, and z2 for second electron. Right? So on the previous slide, we were dressing this kinetic energy operator with bra and ket for second electron. So do you see this under brace for the first line? So the first portion is kinetic energy for electron 1, so T sub E1. And second combination of terms is kinetic energy for second electron, T sub E2. So let's consider application of this phi2 from left and right to each of them. So if we do apply this bra and ket procedure averaging over electron number 2 for the kinetic energy of the first electron, it is what is shown in the middle of slide in the brackets. I can hear you, but if you really have a question, please speak louder.
Okay, so in the previous slides, when you had all 6 of those terms up, you just simply swapped phi1 and phi2.
Let me go to this slide and you here?
Yes, so you just simply swapped phi1 and phi2?
No, I didn't swap. Do you agree with the first line on the slide that is up now? Or I need...
Yes.
If you agree with the first line, the rest is technical. So I declare intention to swap phi1 and phi2 at a later stage, but right now we are not doing it.
Okay.
Right now we only convolute, we only multiply left and right part of equation by phi2 from the left.
All right.
To integrate away dependence on phi2 to get an equation that will give us equation for phi1.
got it, got it.
Okay, good, thank you. Okay, so now, if you look inside this little box, the kinetic energy of first electron, this operator, does not change wave function of the second electron. Therefore, the phi2 bra vector and T sub E1 operator can be swapped, because T sub E1 operator doesn't affect second electron. So we put it out of Bryant ket. And then we see that phi2 and phi2 Bryant ket are orthogonal and they give 1. So if we perform procedure of averaging over second electron for kinetic energy of first electron, it doesn't change. So you see, it equals T sub E1, right? But now, in the last line of the slide, we are going to apply the same procedure of finding expectation value to the kinetic energy of the second electron. Here we cannot swap anything. Here this kinetic energy, which is just derivative of a position, will change wave functions, and upon completion of this operation we will get a number. We will get an expectation value of kinetic energy of second electron. But for us it is important that it is not operator anymore. It will be a number. So upon averaging procedure, kinetic operator will be composed as a summation of T sub E1 as an operator and expectation value of T sub E2 as a number. Okay? So the same protocol, the same procedure is applied to potential energy terms. I do not have them typed in, but the idea is the same. So there are, for the attraction to nucleus, for example, if it is H2 molecule, if there are two ions, R1 and R2 capital, and 2 electrons, there will be 4 terms, minus 1 over R1 minus R1 capital, and so forth, all combinations. So in case the term does not include position of second electron, so I'm looking on the line number 2, phi 2 V sub N1 R1 phi 2. Then 1 over delta R, 1 over R1 minus R1 capital can be put outside of a brackets, and second wave function will be averaged out. So we will get an operator. So it will be operator of potential energy of attracting first electron to first nuclei. Then, if we take the attraction of the first electron to the second nuclei, same story. We can put 1 over delta R out of brackets, use property of orthogonality, and it will be again 1 electron operator, which shows how much first electron is attracted to second nuclei. But when we will deal with attraction of second electron to first and second nuclei, then this procedure of finding expectation value will convert this operator into a number. So it will be matrix element of 1 over R2, so it is circled in the little red circle, minus R1 capital with phi 2 bra and cat on the left and right. So it will be expectation value in angular brackets V sub N1 E2. And the same for the attraction to the second nuclei. So if we consider attraction between electrons and nuclei, we also convert part of terms into numbers, and part of terms become one electron operators. Okay? Now let's look on the... So everything before was really easy, trivial, and no challenges. And the last term, it will be not much writing, but it is most challenging, and it brings most complications for any theory and programming. So now we are considering electron repulsion. 1 divided by difference of position of first electron and second electron. And we do not have any constants in front because we are working in atomic units. So if we take this interaction between electron 1 and electron 2 and find expectation value in respect to wave function of second electron, it means we perform integration of this 1 over R1 minus R2 over R2. And the 1 over R1 dependence will still be there. Hi Mary, how are you? Did you just join or you were listening before?
I just joined. Can you hear me?
Yes.
Okay, I just joined. Sorry, I was at dinner.
Oh, not a problem. I hope the recording could be working this time.
Yeah, no, it looks great. I see some slides.
That's good. That's good. I am about to finish very soon, so you have just 5 to 10 minutes to concentrate, and we will be done.
Okay.
So electron repulsion is most challenging term, and it depends on 2 variables: position of first electron and position of second electron. But now we perform this bra and cat averaging over the second electron. So the resulting object will be neither 2 electron operator nor number. It will be like partial hybrid object that will be acting as operator only on electron 1, only on variable R1. And it is not much writing, it is more like conceptual. If this idea of hybrid object that acts only as 1 electron operator is okay for you, then everything is great. So now we need to subtract all objects which are not operators from energy. And then we will have standard composition of left part consists of operators and unknown wave function, and right part consists of eigenvalue and unknown wave function. So the numbers that we need to subtract, that the numbers that did convert from operator form into form of expectation values are kinetic energy of electron 2. So I'm looking this. This slide has 2 lines, and I'm 2 lines with equations, and I'm declaring the first of them. So eigenenergy number k with tilde is eigenenergy k for multi-electronic stuff, wave function, minus expectation value of kinetic energy of second electron, minus expectation value of potential energy of attraction of second electron to first nuclei minus expectation value of attraction of second electron to second nuclei. Now we come to the question of Kevin. I apologize for being lazy, but suppose that I write absolutely the same equations, but swapping first and second electron, deriving equations for the second electron wave function. Then we will do the same procedure, and unknown eigenvalue for the second electron wave function, we'll have this E with two tildes with 2 electron eigenvalue minus kinetic energy of first electron and potential energy of attracting first electron to first and second nuclei. Okay. And now we do have, actually I do not need this slide, I have it in a better form. Now we do have two equations. Let's look on the first one. So the first equation has standard form of time-independent Schrödinger equation, where in the curly brackets we do have an operator that depends only on independent variable R1. It acts only R1, and it is equation for a known function phi 1. On the right side, we have this E with tilde, which is defined based on subtracting expectation values. Okay? And inside the curly brackets, it was a little intrigue that we declared at the very beginning of the lecture. There is a kinetic energy portion affecting electron 1, potential energy operator that reflects attraction of first electron to all nuclei, and this crazy term of electron-electron repulsion with averaging over wave function of the second electron. So here, to process further with this first line, with this equation, we need to assume that wave function for the second electron is already provided to us from someone knowledgeable, from some other procedures. And if you know this phi 2, then we can solve for phi 1 and later on find multi-electron wave function as a product of phi 1 times phi 2. Now we are coming to the, again, coming back to original question of Kevin. What if we swap first and second electron? Now let's say if someone provided us, someone knowledgeable provided us function phi 1, then we can formulate an then we can go to the second line on this slide and formulate an operator in the curly brackets, which will act only on second electron and which will include averaging over position of first electron in the first wave function. Okay? So basically it is the last slide. It is not much writing. We are not doing derivations. It's just wrapping our minds around the idea that we are trying our best to practice separation of variables. And instead of equation for 2-electron wave function, we are formulating small, simplified, reduced dimensions equations for 1-electron wave functions. Today, we used oversimplified example of only molecule with only 2 electrons. But generally, there should be no problem for like 5, 10, 100,000 electrons. Equations will be the same. And the feature of these equations, the most complicated thing, is the electron-electron repulsion. So it is background repulsive field created by all but one electrons. So if we have electrons in addition to our electrons that we describe, all other electrons, they form distribution around nucleus, and they create average repulsive field that works against our poor last electron. And this repulsive field of average distribution of all other electrons is a major challenge of the computational chemistry. So all theories are just dealing with different level of approximations how to describe electron-electron interaction, this average field exposed by all electrons to our last electron. Okay, I'm done. So please ask your questions if you have any. If you're not ready to formulate them right now, just but you may have them. Feel free to ask them by email. And I have already sent the slides. They have list of sign-up subjects for presentations and a little update on homework assignment. If you didn't complete and didn't email it by now, you just add a little calculations on simple objects and send it as a Word file or PowerPoint, or bring it just in a printed form in class on coming Tuesday.
Can you hear me?
Yes, I can.
Okay, finally. Sorry, I was having trouble with my mute button. For the homework that's due today, I think there was a typo in the slides. I'm not sure if
extra credit for any typo that you find. You can report it in writing.
And okay, I'll send it to you, the homework, what I think it means.
Good.
Because it didn't quite make sense to me if the way you showed us you showed it as multiplication and then you showed it as plus.
Uh-huh.
And then in the homework, and that's where I got a little confused. So I'm just going to send you what I think is what you were looking for. But please let me know if I misinterpreted. I'll just
yeah. This is fine. Okay. This is fine.
Okay.
Yeah. Thank you much.
Excellent.
So there will be no lab tomorrow. You can come to the class; it will be open, but I will be not showing up. There will be another activity. But on Thursday, I will come in the same format. I will appear online and show some slides and explain them.
Okay.
Okay?
Perfect.
Okay, thank you much.
Right.
Have a nice evening.
You.
Meeting is dismissed.
All right. Bye-bye.
Bye-bye.